Okay, welcome back. So now we're going to consider the issue of interaction and confounding. So when a covariate z is associated with both the outcome variable and the primary independent variable, that is the risk factor, then the relationship between the risk factor and the outcome variable is said to be confounded. So by using this model, the model is beta naught plus beta 1x plus beta 2z, as we did in the previous example, we can adjust for confounding. But this method can only be used when there's no interaction. Okay, so let's first describe a situation where interaction is absent. Okay, so let's let the risk factor x be dichotomous, exposed or unexposed, and we'll let the covariate z be continuous, like age. Now, if the association between the covariate, age, and the outcome is the same within each level of the risk factor, that is within each exposure group, then there's no interaction between the covariate and the risk factor. Now, graphically, the absence of interaction yields a model with two parallel lines, one for each level of the risk factor. So this is what we mean by no interaction. You have the exposed group and the unexposed group. And we can talk about what is the logit in the exposed group, what is the logit in the unexposed group. And I can talk about the difference in the logit. And remember, the logit difference is the log of the odds ratio. So to say there's no interaction says that the log odds ratio is the same for people of young age, middle age, and old age. It doesn't matter. And if the log odds ratio is the same, it means that the odds ratio is the same for individuals in each group. That means no interaction. But when interaction is present, then the association between the risk factor and the outcome variable is not constant over the levels of the covariate. So that is, the covariate modifies the effect of the risk factor. So here's an example where the logit difference is not constant over all ages, and that would suggest you have interaction. So here you can see that the difference between the logits at young age is like this. At old age, it completely crosses. Okay, so in one case, the odds ratio would be less than 1. In the other case, the odds ratio would be considerably greater than 1. So we have interaction because the odds ratio and the log odds ratio, the logit difference, is not constant over the levels of age. So any statements that you would make, if you have a situation where there's interaction, any statements that you would make is all about which age you're talking about. So you can't make a global statement like I could here. I mean, I could make a global statement. I could tell you what the odds ratio is controlling for age. I can't control for age here because every age is different. So I'd have to talk about what happens at each age. It's very important. So we have to understand whether we're in a situation of effect modification, which is this, interaction, or if the lines are parallel, in which case there's no effect modification, and then I can talk about confounding. Okay? So in general, we have the logit, let's say this is the risk factor and age. The logit is beta naught plus beta 1 times x plus beta 2 times a times age. That's the model. This model assumes the lines are parallel. Okay? So for group 1, that is for people with x equals 0, we have that the logit is beta naught plus, this is 0, plus beta 2a. For group 2, that is for x equal 1, we have the logit is beta naught plus beta 1 times 1 plus beta 2 times age, which is beta naught plus beta 1 is equal to beta naught star. It's simply some new intercept term, but the slope, beta 2, is the same. So in this model, we have the same slope for both group 1 and group 2. That suggests no interaction. But if there is interaction present in the model, then we have to use this model that has x, it has a, but it also has the interaction between x and a. And the interaction is literally the product of the two variables, x times a. And we include that as a third variable in the model. Okay, so then for group 1, we see that the logit is beta naught plus beta 1 times 0, which is 0, plus beta 2 times a, plus beta 3 times x times a, and x is 0, so the last term falls out, and we're left with beta naught plus beta 2 times a. If we're talking about group 2, for group 2, individuals in group 2 have x equal 1. So there we have beta naught plus beta 1 plus beta 2 times a plus beta 3 times 1 times a. So it's beta naught plus beta 1 is sort of the intercept term, And beta naught plus beta 3 times A is the slope. Beta naught plus beta 3 is the slope. So we know that our way of being able to test whether the two groups have the same slope is to simply test the hypothesis that beta 3 is equal to 0. Because if beta 3 is equal to 0, then this term goes away, and we're left with a slope of beta 2, which is exactly the same as the slope that we had in group 1. And if the slopes are not equal and interaction exists, then in fact beta 3 will not equal 0. So if the slopes are not parallel, if there's different slopes, if you have interaction, then beta 3 will not be equal to 0. Okay? And how do we determine whether beta 3 is equal to 0? Well, of course, in logistic regression, we're going to use a likelihood ratio test. And so it's going to be very easy. We're going to have to fit two models. We're going to fit a model that does not contain the interaction term, but it contains everything else. And we're going to put another model that does contain the interaction term. And we're going to test the hypothesis that beta 3 is equal to 0 using a likelihood ratio test. So in the previous example, age was an effect modifier because it modified the effect of the risk factor. And again, when we have an effect modifier, we first have to specify the level of the covariate before we estimate the odds ratio of the exposure and disease. Okay, so let's take a few examples. Here's the first example. We have dependent variables, coronary heart disease, and we have sex. We want to know whether males and females differ with respect to CHD. But we also know that the groups as sampled may not have the same age. So we want to control for age. Okay? So we fit this sequence of models. So the first model contains only sex in it. And here are the coefficients. Beta naught is minus 1.046. Beta 1 is plus 1.535. If you take e to the 1.535, you get 4.64. So in a crude sense, the odds of CHD is 4.6 times higher for males than it is for females. Okay? Again, it's crude. I've controlled for nothing. So now, again, my worrying about age gets sort of dealt with by including it as a covariate in the same model. So I put age into the model. And when I put age in the model, then my new model becomes beta naught. Here's beta 1 times sex, and beta 2 times age. So I put it into the model. And notice that after I control for age, the coefficient for sex decreased from 1.535 before I controlled for age to 0.979 after I controlled for age. So this change in the odds ratio from 4.64 crude to 2.66 controlling for age suggests that age is potentially a confounder. Anytime in our book, we recommend that anytime you see a change in the odds ratio, well, actually a change in the log odds ratio, but also you can think about it as the change in the odds ratio of more than 15 to 20%, we would say that the variable is potentially a confounder. And so in this case, you know, the change is far more than 15 to 20%, and so you can really suspect that you really need to control for age if you want to talk about the difference between males and females with respect to CHD. And to see if there's effect modification, we then build the full model that includes the interaction term. Okay, so now model 3 contains the sex, contains the age, and it also contains the interaction between sex and age. Okay, and now to determine whether beta 3, now this is the first time, by the way, that I've said anything about a statistical test. Okay, I mean, determination of confounding has nothing to do with p-value. Determination of interaction has everything to do with p-value. So to determine whether beta 3 is equal to 0, I do a likelihood ratio test where I take minus 2 times the difference in the log likelihoods. The log likelihood for model 3 is the one that contains the interaction term, and here's the log likelihood of model 2 that didn't contain the interaction term but contained both age and sex. And you can see that this likelihood ratio test value, the statistic is 0.52, and that's compared to a chi-square distribution with 1 degree of freedom, P-value is very big, 0.47. So we don't have evidence to reject the null hypothesis. So we believe that beta 3 is probably equal to 0. And as a result, we conclude that age is not an effect modifier, but it is a confounder. And so we need to use model 2. Okay, is that clear? Okay, now let's take a second example, but we'll do that after the break. So let's take a break, and then we'll look at another example of confounding and effect modification.